A very good morning, one and all. Welcome to the session number 23. In this session, we will learn about LCR parallel circuit. In the last class, we learned about LCR series resonance circuit. The condition for series resonance circuit is omega L is equal to 1 over omega C. Then the resonating frequency was given by nu r is equal to 1 over 2 pi square root of L into C. A series resonance circuit is also called as acceptor circuit because it admits maximum peak current through it at resonance. Q factor, which is defined as the ratio of voltage across L or C to the applied voltage across R, which is given as omega R divided by 2 delta omega. In terms of inductance, resistance is omega R into L over R. Bandwidth, which is the difference between the upper and lower frequencies. Omega 2 minus omega 1 is equal to 2 delta omega. The learning objectives of this session is LCR parallel circuit and admittance. By the end of this session, we will learn about LCR parallel circuit and the term admittance. LCR parallel circuit. Let us consider a resistance R, capacitance C, inductance L are connected parallelly to an external AC source with an voltage epsilon is equal to epsilon naught e power j omega t. Using phasor diagrams, we know that the voltage and current, they are in phase for resistance. Voltage leads the current in case of inductance, whereas in capacitance, current leads the voltage. For a parallel circuit, I let IR, IL and IC be the current flowing through the parallel circuit in resistance, inductance and capacitance respectively. The vector impedance is the sum of R, C and L, where R is represented as ZR, J omega L, which is due to the inductance, is represented as ZL, and 1 over J omega C, which is minus J over omega C, that is due to the capacitance C, which is represented as ZC. Now the total current at any instant is the sum of the currents in resistance, inductance and capacitance. Therefore, I is equal to IR plus IL plus IC. Using Ohm's law, epsilon over R plus epsilon over IL is epsilon over J XL plus epsilon over minus J omega XC. Now, taking epsilon common, we represent epsilon into 1 over R plus 1 over J XL plus 1 over minus J XC. Taking J out common, this can be represented as epsilon into 1 over R plus J into 1 over XC minus 1 over XL. This is like a complex number. It can be represented as G plus J BC minus BL. BC is 1 over XC, which is called as capacitive susceptance, and BL is equal to 1 over XL, which is called as inductive capacitance. Now the total current, which is we represented as G plus J into BC minus BL, which is the required rectangular form. Now the admittance can be obtained using the modulus of this one, which is given by mod Y, which is equal to square root of G, which is 1 over R square, plus omega C minus 1 over omega L whole square. The current in this circuit, which is given by I is equal to epsilon into admittance, which is given as epsilon into square root of 1 over R square plus omega C minus 1 over omega L whole square, and this particular term is called as admittance. Depending upon the value of omega C and omega L, there is a phase difference between current and voltage, which is represented by theta is equal to tan inverse of omega C minus 1 over omega L over R. In case if omega C is greater than 1 over omega L, now the potential across C is greater than the potential difference across L, hence the current leads the voltage by an angle theta. If omega C is less than 1 over omega L, then the potential difference across C is less than the potential difference across L, hence voltage leads the current by an angle theta. It's given by theta is equal to tan inverse of omega C minus 1 over omega L over R. In this session, we learned the parallel LCR circuit. In rectangular form, it is given as I is equal to epsilon into 1 over R plus J into omega C minus 1 over omega L. 1 over R is represented as G and omega C, and minus 1 over omega L is BC minus BL. And the admittance is given as Y is equal to square root of 1 over R square plus omega C minus 1 over omega L whole square. The current in the circuit is given as I is equal to epsilon into Y is equal to epsilon under the root 1 over R square plus omega C minus 1 over omega L whole square with a phase difference theta is equal to tan inverse of omega C minus omega L over R. The parallel combination of inductor and capacitor is called as tank circuit. LC are said to be parallel when they are connected between the same two points. The angle made between the current in the inductor and the capacitor is 180 degree. In a parallel combination, the phase angle between voltage and current is 0. In parallel combination, voltage across the circuit elements remains same. That's all for this session. Thank you all.